something I should have mentioned in the mandatory meeting earlier. This is the textbook for the course. This is a book called The Art of Electronics by Horowitz and Hill. This is one of the great textbooks in physics education. I would imagine that close to 100% of experimental physicists own this textbook, which is really rare. I have owned several of these copies. This is third edition. I've owned all of the editions, actually, of this book. It is a great book. However, students have issues with it. I want to be frank with you. I'm not going to insist that you actually buy it. I strongly suggest you buy it. It is the required text, but it's expensive. Much of it is online in some form or another, I think, and for free. So this book is funny, believe it or not, and opinionated, which is great if you're a practical person trying to do circuits. But I understand, it's difficult for me to put myself, frankly, in the position of students. So I understand the problem that students have with this book is that it sort of assumes a little bit that you know what you're doing already. Okay? And so that's why I'm hesitant. I'm not going to say you have to go out and buy it. But it is a great book, and if you stick in experimental physics, for the last 30 years, actually, people of all experimentalists have owned the book. I won't say any more. You can take a look at copies of it, look at it online. Keep in mind there are 3 editions, and if you go and buy a second edition book, they're probably more common. I'm sorry, if you try and get a second-hand copy, probably the second edition is more common because this came out relatively recently. Okay. Why these things? Somebody once said that lecturing is a great method of passing information from the professor's notes to the student's notes without it going through the minds of either. There's a lot of research on modern methods of teaching. A lot of it curiously comes out of physics and has been adopted in many places, like those clickers that you probably despise. That comes from research on physics classes. And the idea is that you can make students think about the material during the lecture. They're much more likely to retain it than if it's just me sitting here spewing information at you. So every now and then during these lectures, a couple of times, I'm going to stop the class. Well, I ask you a question, stop the class, and then ask you to discuss the questions that I have asked with your fellow students in groups of a couple. I don't really care about the size. And just try and come up with the answer to that question. Sometimes those answers will require you writing things down. That's what the boards are for. It also means that I can pass through the class and just glance at people's boards and see if people are on the right track. One of the pieces of data that I once saw at a conference on teaching was a graph of 24-hour brainwave activity. And what do you think was the only activity in which people's brain waves were less active than sitting in a lecture? It's not sleeping. It's watching TV. So that's why I use them. I think it's kind of fun. It gives a pause and a break to the lectures, lets you guys rattle around in your seats, lets me stop, regain my voice and things like that. So that's why I use them. Okay, so let's get started here. This information is not us. I don't know who it was. This lecture is going to be, in large part, a review of material that you should have gotten in your 7B class, or your 7B equivalent. A lot of you are new students here to Berkeley, and welcome. for those of you who transferred in. But a lot of this should be a very fast-paced review of some of the things that you've seen in 7B equivalent. And I'm also going to be discussing some concepts, very useful concepts, which will show up very soon in your labs, which I don't believe you would have seen back in 7C. But we're going to start at the basics of circuits. And the most basic thing that we can talk about is a power source, a voltage source, for instance, which I'm sure you've all seen as a symbol, which looks something like this. This is a voltage source which has a voltage V across it, and it has a sign to it, because one side of the thing, this source is positive, one side is negative. Often the voltage, the plus and minus, are emitted, and the only way you can tell which is that the plus sign has a larger line than the minus sign. Also commonly, you'll see voltage sources done another way, which is like this. It's exactly the same thing. It's more common in circuit diagrams that come from Europe in some sense, but never mind this. But in any case, what does this actually mean? What do we mean by a voltage source? A voltage source, an ideal voltage source, is a device for creating an electrical potential difference. That's all it does. It means that if we measure from here to here, we're going to see a potential difference which is equal to V. Okay? Simple enough. Sometimes, particularly on older circuit diagrams, you'll see something that looks like this. Any idea what that is? Yes?
A bunch of sources put together in series.
That's right, but that is this. What is this? You can all see it, right? It's a 9-volt battery. Chemistry is a truly boring subject. And there's only a few things you really need to know from chemistry. One of them is, what is the typical energy of a chemical reaction about? First of all, what units should chemists use? They don't always, but there's only one sensible unit. Electron volts. Okay, that's the only sensible unit that you should ever discuss chemistry in. So what is the typical scale of a chemical interaction? No. One interaction. What's the binding energy of any atom? Yes?
About 1 eV.
1 eV, that's right. That's all you need to know about chemistry. The rest of it is details. Or 1.5 eV. It turns out that almost all batteries have some chemical reaction which is on the order of 1.5 volts. Okay? Some of them are 1.2, some of them are maybe up to 2. Those are rare, but it's 1.5. That's why your A, AA, AAA, D, C cells are all 1.5 volts. So what is this? This is a 9-volt battery. What's inside of this? 6. 6 1.5 volts stacked one on top of the other. And that's what this old symbol used to mean. It used to mean that you could stack things together and get more voltages out of it. Okay? But this is really obsolete. And this was more important in the days of tubes, believe it or not, where there are actual batteries which were common, which would put out 100 volts. I think they were called B batteries. Is that right? Do you remember what the 100-volt batteries were called? B cells? No. Never mind. Doesn't matter. Okay, so those are our voltage sources. Okay. What's next if we want to make a simple circuit? Well, we obviously need some wires. So here's a voltage source, and here are wires, like this. Okay? So, wires are ideal conductors. Anybody want to tell me what the definition of an ideal conductor should be? Yes?
No resistance.
That's true, but that's a subtle concept. I don't know what resistance is yet. Well, all right, I'll pretend that I know. What about
Constant voltage.
constant voltage?
That's voltage difference across any 2 points is 0.
That's right, that's what I'm after. An ideal wire is something that if you measure the potential at 2 points on that wire, no matter how much current might be flowing through that wire, the potential drop is 0. And that's what our ideal wire is going to, that's what our definition of a wire. That does not mean that the potential of this wire is 0. In fact, in this case, this potential might be 0, but that would mean that this wire is at 1.5 volts. Okay, so the potential on a wire need not be 0, but the potential drop across the wire is 0 and independent of the number of electrons which are flowing in that wire. Okay? So the next concept, if we're going to build a circuit, the next sort of thing that we're typically interested in is, well, okay, how many electrons are flowing in that wire? And the next thing I'd like to consider is something called a sink or a source. A sink is something that just absorbs electrons coming from all directions, like that. Can there be a point in a circuit which is a sink? Why not? Yeah.
The current has to go somewhere. You can't just have a single absorbing all the
Right, the current has to go somewhere, and that's because of conservation of charge. If I have charge pouring into one place, then charge clearly wouldn't be conserved in this one place. So a sink is not possible, nor, by the way, is a source in which current is flowing out in all directions. Right? Nonetheless, kitchen sinks exist. And electronic sinks and sources also exist. They're very common on circuit diagrams. But there's always a trick. Just like in a kitchen sink, the water doesn't really disappear. It goes down the drain. In an electronic circuit, if you have a sink or a source, the water doesn't actually, the charge doesn't actually disappear. It goes somewhere. But nonetheless, it's often useful to think about sinks or sources. So we'll just keep that in mind. Now, can anybody think of an exception to this, making a sink or a source?
Current goes back to where it came
I'm sorry?
from. The current's going back to where it came from.
Well, you're maybe sort of going in the right direction. Yes?
If you have temporary
Temporarily, you can do this with a capacitor. If you have an alternating current, a current whose changing sign backwards and forwards, you can temporarily have a sink or source, but not for very, very long. Okay, so we've got many of the elements that we need to make a circuit. We have sources of potential, we have wires. So let's build a circuit. Well, first of all, one has to realize that in a circuit, what's the word mean? A circuit is something that goes around in a circle, right? Horse racing circuit. How many of you have ever been to a horse race? I've never been to a horse race, bad analogy, but okay, things go around in circles. So we have to build something where the current goes around in a circuit, okay? So what can we do? Well, there's another sort of circuit element which resists the flow of electrons. What is that called? A resistor. So resistors are given this particular symbol and a value which is called a resistance R, like this. And this is a particularly nice symbol because this is a tortuous path which gives you an indication of what the electrons have to go through. Unfortunately, I spend a lot of time at CERN in Europe, and Europeans have a truly awful symbol for a resistor. They draw them like this. This removes any of the visual connotation of what it's actually doing, but if you see this on a circuit diagram, that's right, what is resistance. Now resistance is of course are measured in ohms, voltages were measured in volts. So we can build a simple circuit, and a simple circuit would be this circuit over here, V, R, and if we want to figure out how much current I is flowing through this, I hope that I don't have to remind too many of you that the current is given by Ohm's law, which is, there are many ways to write it, V over R, or the voltage is equal to the resistance times the current, like this. Okay, Ohm's law, you all saw that before, right? Now, Ohm's law is a peculiar law because it has a linear relationship between the current, I, and the voltage V. That constant of linearity is the resistance, R. So, for the first time we're going to deviate, I think, from 7b. I'm going to ask you a simple question. Why is Ohm's law linear? Why should it be a linear relationship? Why should there be a linear relationship between voltage and current? You've all seen it that way, but did you ever stop to consider that it's linear? And that's a rather special thing, right? In the universe of laws of relations I could have written out there, that's just one unique one amongst, well, an infinite number. So, what I'd like you to do, you won't need your boards for this one, but I'd like you to spend a minute or two discussing with your neighbors why you think Ohm's law is linear. That was an invitation to talk. Okay. Like in many of these questions, times where I'm going to ask you to work something out on a board or come or talk to your friends and come up with an answer, the pedagogical reason, for some reason that's a word I can never pronounce, but the teaching reason for doing this is not necessarily for you to come up with the correct answer, but it's just to get you thinking about the problem. It wakes your brains up, okay? Does anybody know what the correct answer to this problem is? It's really brief. Yes?
Is it that it's not always actually linear, it's just an approximation?
Very close to the correct answer. The correct answer to this thing is that things which have a linear relationship between the current and the voltage are called resistances and they obey Ohm's law. And things which don't obey Ohm's law. In other words, it's a trick question. And let me tell you, the fun doesn't come from things that obey Ohm's law. There's only so much you can do with resistors, and they're generally pretty boring things. The fun comes from things which have a nonlinear relationship between the current and the voltage, and that's what we're going to spend the bulk of our semester studying. Things like diodes and transistors, and eventually operational amplifiers, in which this isn't followed. So, there's nothing intrinsic about Ohm's law, really. It's a property of certain materials under certain conditions. Nonetheless, it's still a very useful thing to have resistors. For instance, here is a resistor. I doubt that too many people can see it, but what it is, there's a small body from here to here, which, unless you have sharper eyes than me, those of you in the back row can't see it, and two leads on either side. It's a resistor. Okay? And this resistor is probably linear over something like 5, maybe even 6 orders of magnitude of current. In other words, really quite linear for this particular thing, maybe less. You could certainly get things which are linear over 6 orders of magnitude in the current. Now, resistors come in an enormous variety. If you go to a company like DigiKey, which is one of the big suppliers of electronic parts in this country, they probably sell on the order of 100,000 different types of resistors. That's a lot. So what are the differences between these resistors? Well, there's the obvious difference between resistors. What's their resistance, right? So you can commonly get resistors that are, say, run from about 1/10 of an ohm or so, up to something like 100 megohms. Now you can get lower ones and you can get somewhat higher ones, but that's the common range. And they're spaced by, on the order of 1% differences. So you can see immediately if I'm going over 7 orders of magnitude with 1% differences between them, there's going to be a lot in that series. This one happens to be an 820 ohm resistor. I can tell that because there's a color code on these resistors. This is gray, red, brown, and then silver, and that tells me that this is an 820 ohm 10% resistor. But you need to memorize that color code. You won't, it'll take a while. Okay? So the colors will just tell you what it is. It's really convenient to have that memorized. But anyway, this is 820 ohms, which is very, very close to 750 ohms, right? This is a 750 ohm resistor. Now, they're different. Do you think it's the resistance that makes the difference between these two resistances? Between these two resistors? What do you think the difference is? The material, to be sure. This probably is made from carbon, and this is probably made from tungsten, would be my guess. Tungsten wrapped in a ceramic form.
Current?
The current in what sense?
And how much it can take.
Yes, that's correct. Resistors are also rated in power. This can take about 1/4 of a watt. It will actually get quite toasty at 1/4 of a watt. If you put in much more current than that, it will burn out. This, on the other hand, hey, it's not even labeled. This is probably a 100-watt resistor, maybe a 200-watt resistor. So this can take on the order of 100 times as much power as this one. So resistors come in different powers, which is part of the way where we get to 100,000 resistors being sold by DigiKey. The power rating is often important. For instance, I have a resistor over here. It's a 2.5 ohm resistor and a 5-volt power supply. And I'm not sure how well this is going to work. I'm going to turn it on and watch carefully. Watch carefully right over here. It's nothing that dramatic. There's a yellow-green LED that's going to turn on. And you know what? This is a big failure. I'm actually surprised. Anybody smell anything? Do you guys smell anything back there? Oh, now we're getting the smoke. That's what I was after. Do you see? Oh, everybody see the smoke? That's what happens when you put too much power in a resistor. You know, there are sophisticated explanations for how electronic components like transistors work, but they're all wrong. The actual answer is they work on smoke, because when the smoke leaks out, they stop working. But oh, now this is what I was after. Oh, come on. This was working a minute ago. Do you see it? It's not glowing. You see it's glowing red? Mm-hmm. Right over? I don't know. Okay, it caught fire. This is generally not good. And by now, I can smell it over here.
Oh, yeah.
Can people smell it? Undoubtedly, I've just taken 30 seconds off of all of your lives. The smell of burning electronics is a smell that you should learn to recognize. Okay? It's a distinctive smell. It's not an uncommon smell, even in the real world. Well, if you call CERN, for instance, the real world. I think about 3 times while I've been at CERN, we've been in our control room, where that smell has come wafting over. Including once when an entire rack of equipment caught fire. It's best to catch it early, which is why, actually that smell is a little overpowering now where I am, which is why it's good to know what that smell signifies and react to it before your equipment catches fire. Because when that catches fire, you generally have much worse a mess on your hands and much more expense than if you can catch it while it's still at the smelling stage. Okay, so that's why there are so many types of resistors. Okay, now I'm going to probably, well, we're going to plunge straight into a really fast review of things, okay? Resistor circuits. Here's a circuit. It's got 2 resistances in it. Okay, voltage V, R1, R2. And we'd like to know what the current is flowing through this circuit. I'm sure you've all seen this before. The best way to think about it is from here to here. I have a voltage V1, which is equal to, God, that smells awful, R1 times I, okay? And from here to here, well, you can use the same point because anywhere along the wire is at a potential, the same potential. We have V2 is equal to R2 times I. How do I know the current is the same going through both of these resistors? Which means, where else is it supposed to have gone, right? So the current has to be the same, and the voltage clearly has to equal the voltage of the battery, so we can trivially write that V is equal to V1 plus V2, which is equal to R1 times I plus R2 times I, which is equal to R1 plus R2 times I in quantity like that. So I can define an R total times I, where R total is equal to R1 plus R2. And that's a result that I hope you do remember back from your 7B classes, that this resistance, where you have 2 resistors in series, is just equal to the sum of those 2 resistors. Resistors in series add. Now, I'd like you to consider a case where R1 is equal to 1 ohm. That's the symbol for ohm. It's omega in the Greek, capital omega in the Greek alphabet. And R2 is equal to 100 ohms. And there's a real quick discussion between you and your friends. Can you tell me what the total resistance is in this particular case? So talk. Okay, that's enough for this particular question. What's the answer? 101. No! That also wakes people up if I scream. I also throw chalk at people.
Why me?
The total resistance in this case, stumbling over chair. By the way, I once fell off this table because this moves up like this. That was not fun. The total resistance here is not 101. Does anybody remember when I called off the value of that resistor, what I said? I said it was 820 ohms, but I also said something else. The tolerance was 10%. The resistors that you have in the lab are 5 and 10% resistors. If you add something that's 100 ohms with 5% range, it's going from 95 to 105. If you put that in series with a 1 ohm resistor, the resistance is 100 ohms. Now, some of you are mathematicians. I suppose somebody has to be a mathematician. Will tell me that it's a little more accurate to say it's 101 plus this, well, for about 14%. Not 14%, excuse me, slightly over 10% now. And that's technically true, but this is a physics class, not a math class. And so it's 100 ohms. It doesn't make any sense in terms of designing and building circuits to worry about things like this, like that is 101. It will slow you down. It's not going to be any more accurate, so why keep it? If you want to make circuits which are accurate to 1%, go out and buy yourself 1% resistors, which are actually quite common these days. If you want to make a circuit which is 0.1% resisted, accurate, well, the first thing you're going to need to do is to go to Washington to get yourself a bigger budget, because 0.1% resistors are quite expensive. They'll go from a penny a piece to $10 a piece very quickly. So think of a better way. But in any case, we need to think about these sorts of ratios. Half of what I'm trying to teach this semester is for you to look at a circuit and be able to discard information. One of the pieces of information that you need to discard is when you've got two resistors, but one is much bigger than the other. Let's just ignore the bigger resistor for this purpose anyway. The next thing I'm going to be discussing is not parallel resistors. It's actually a slightly more complicated combination here. I'm going to have a battery like this, and two resistors like I had before. That's an R, believe it or not. Here's R1, and I'm going to want to know what the voltage here is. We'll call this V0, the battery voltage. I'd like to know what the voltage is between these 2 points under the condition that there's no current flowing out of V. And under that condition, it's really easy to figure out what that voltage is going to be, all right? Because we've already figured out what the total resistance is, so we can figure out what the total current is. Well, forget the total current, the only current. The current I is going to be equal to V0 divided by R1 plus R2, so the voltage drop here is simply going to be equal to R2 times I, which is equal to R2 divided by R1 plus R2 times V0. In other words, it's going to be a fraction of the original voltage. Since the voltage is lower than the original voltage, this is a circuit element which is called a voltage divider. This is an exceedingly common circuit element. And another thing that I'm trying to teach you this semester is to be able to recognize voltage dividers, because they show up all the time. Sometimes they're disguised, but you want to be able to recognize a voltage divider in a circuit and instantly recognize that that's what it's doing and that's why it's there. Now let's talk a little bit more about what this does in certain cases. What happens when R1 is equal to R2? What then is V going to be equal to? It's going to be equal to 1/2 times V0. All right? Let's take another case. Let's take the case where R1 is, why don't we do this case? R1 is much, much bigger than R2. What is V? Well, this is a big number in the denominator, because R1 is big, and this is a smallish number, relatively speaking. So you could say it's equal to 0. But that's a little bit too crude. A little bit less crude is to say, okay, I can't really discard R2 and stop thinking about it but in the numerator, but I can discard it in the denominator, right? If this is 100 and this is 1, what is their total sum? 100. So I can ignore this. So V1 is R2 divided by R1 plus R2 times V0, but I can ignore this, and what I actually have is R2 divided by R1, which is some very good approximation, times V0. Okay? A simplification. What about the case where R1 is much, much less than R2? The other limit, V, is going to be equal to R2 divided by R1 plus R2 times V0. Anybody care to tell me what this is equal to? It's just equal to V0, because in this case I can ignore that. And I've got R2 over R2, which is just 1. So, okay, that's a voltage divider. Really very, very important circuit component here. Now, let's go do that parallel circuit, which I was discussing earlier. So, I mentioned earlier. So here's V, here's R1, here's R2. The total current I is the current that's coming out of the battery, but now I have individual currents I1 and I2 going through each of these resistors, right? There's no voltage drop across a wire, so the voltage here, the potential here, is the same as the potential here, is the same as the potential here, is the same as the potential here, likewise on the bottom. So it's really easy to write down that I1 is equal to, V divided by R1. I2 is equal to V divided by R2. And what is the total current then? Well, the total current I here splits in 2 directions, but there are no sinks or sources. So I has to be equal to I1 and I2, so this has to be equal to V divided by R1 plus V divided by R2, which is equal to V divided by 1 over R1 plus 1 over R2, which says that 1 over R total is equal to 1 over R1 plus 1 over R2, where that means that this circuit could have been represented by just one resistance, which is equal to, well, we'll come what it's equal to, but it's equal to R total. Like that, okay? And so what you conclude from this is that in a parallel circuit, the inverse of the resistances adds together. The inverse of the total resistance is equal to the inverse of the individual resistors. That's actually more general than this. If I had a string of resistors here, this would just be a string of inverse resistances summed up there. One nice substitution is that this is R1 over R2 plus R1 plus R2. If you just fool with that for a minute. Okay, let's talk about some special cases. Talk about this special case where R1 is equal to R2. What is R total equal to in this case? I'm not tricking you here. That's right. Think about it. It's going to be equal to 1/2 of R1, which is also equal to 1/2 of R2. The reason for that is clear. Let's just use some numbers. Let's say they're both 10. 10 times 10 is 100 divided by 10 plus 10 is 20, which is 5. Okay, but we actually could have figured this out, because if I have, these two halves of the circuit are rather independent of each other. If I have a certain amount of current flowing through this one, the same amount of current is flowing through this one, so the total amount of current just has to be the sum of those two things. So the resistance has to be half of that. Okay, what about if R1 is much, much bigger than R2? What is R total equal to? It's just equal to R2. R2 is small, R1 is very large. There's a large current through here. There's some completely negligible current flowing through here. You know, sad to say, never mind. I'm not thinking about it. Any of you guys in the band? No, that's unusual. Certainly nobody here. I was going to make some football remark about Berkeley versus Stanford, but I'm not going to. Okay. Nobody's in the band. Normally I have students in the band. Never mind. Okay. So if one of them is much, much bigger than the other, we just ignore the big one because it's not going to add substantially to the circuit. Okay. Power. We all know about power. It's the only thing Donald Trump wants. By the way, I never make political jokes in class. It would be totally inappropriate. Okay, so here's voltage over here, and here's a resistor like this, a voltage and a resistor. What is the power going through that resistor? 7B. The power could be V squared divided by R. It could be, if I define a current, I like that, it could be I times V, or it could be I squared times R. These are all equivalent forms, and they will give you, they're all related through Ohm's law, they will give you the same amount. Okay? So let's do something a little more interesting with power. I have a battery over here, okay? And it's inside a box which has a resistance R1 like that. And there's a resistance R2 out here, okay? And I'd like to, the battery is fixed. It's got some voltage V naught, let's just call it V naught. And this resistance R1 is fixed. And I'd like to ask you the question, how do I maximize the power being dissipated in R2? Let me give you an example. Are any of you in fraternities? I never make jokes about fraternities either, so this is not a joke, okay? So what is the primary goal of a fraternity member aside from getting drunk? That's not a joke, that's just simple truth. Primary goal is to annoy your next door neighbors by having a jacked up pickup truck and blasting through the neighborhood late at night, waking everybody up, right? Everybody knows this. Is it not true?
Yeah, that's true.
That's true. So here's the stereo. I guess the only place we have stereos left is pickup trucks, right? Here's the sound system. That's the better word these days, right? Sound system in your pickup truck. There's some source it makes, I'm not going to call it music because it's not, it's making noise. And here's something having to do with the circuitry inside. And here's your speaker. So you're trying to make your speaker as loud as possible. So the question is, what size resistance should you use here to annoy the neighbors the most, to get as much power as possible here? So why don't you talk about this with your friends for a bit?
You don't measure across, you measure here.
Okay, any ideas? What size should I make that resistance R2 to maximize the power? Is that a hand up or a stretch? A very big resistor, okay. And what's the logic for making a very big resistor?
It would have more potential.
It would have a larger potential drop across it. We don't, I mean, it's perfectly reasonable to say have more potential, but we don't use that. We just don't. It would have a bigger potential drop across it. But does anybody see a problem with that? Yes?
Right, but what we're looking for is trying to maximize the power, which trying to sort of be represented by maximum potential initial drop. So what happens is, sure, you might get an increase in initial drop, you also get a decrease in current. And because the relationship with between power and current is quadratic and only linear with resistance, by increasing resistance, you decrease the current disproportionately, and so the power dissipated by the resistor goes down. So if you want to minimize the magnitude of the second resistor.
Okay, if I could summarize, the argument, which was mostly okay, was that sure, the potential drop goes up, but the current is going to go down. And the conclusion from that is that we should make the resistance as small as possible, I think, to maximize the power. Anybody okay? Everybody okay with that? Yes, it's the same case the other way around. Sure, now we have a lot of current, but we don't have any potential drop. In fact, that's correct. The actual answer here is that you want to make the two resistances equal to each other to maximize the power. Max power when R1 is equal to R2 here. And we could prove this. I mean, it's not that hard to do. You just write down the formula for the power here, which is you know what the total current is, so you know what the power is here. It's going to be the total current times R2 times I squared. And then you just have a calculus problem to maximize that function. I'm not going to do it, but it will show you that these two resistances have to be equal to each other. All right, actually power is a fascinating subject, and we're going to come back to it later on because it's not at all straightforward, actually. Let's talk about other circuits. Here's a circuit. How much current flows in this circuit?
High.
I'm sorry?
High.
High. Sure. But precisely how much current flows in this circuit?
Maximum current possible.
What is the maximum current possible? It's a battery. All a battery does is produce a voltage drop. So there's a voltage drop from here to here, right? And there's no voltage drop. What? There's no. There's a voltage drop here, and there doesn't appear to be a voltage drop there. Wait a minute. I can do this. Here's a battery. Here's a coin. Coin is a pretty good wire. I just did that. I can do it. Anybody ever do this accidentally? What happened?
Oh, I made like a little solenoid and battery was really, really hot.
Yeah, what I meant to say is anybody ever put, I'm sure you will have because it's just, but it's just what people do. Is to put a 9-volt battery in their pocket with coins. Anybody ever done that? What, you're not nerds? Okay, the answer is the battery gets very hot, the resistor gets very hot. Here, vouch that this has gotten hot. Not very hot yet, this must be a pretty dead battery. I can do it, but what's the difference between this and what I drew on the board? Right. What I drew on the board was an ideal battery. This is not an ideal battery. This 9-volt battery is far from ideal. Any battery has what's called an internal resistance. So any battery actually looks like that. And that resistor will limit the current that can come out of that battery. Okay? we'll come back to this in a bit with some more concrete examples, but that's why that's not a problem. I mean, why I can do it in the real world. Okay? Now, let me talk about another thing. I haven't mentioned this so far. People are pretty comfortable thinking about voltage sources, batteries. That's because we have batteries in our life. But we can also have sources of current. A current source is drawn like this. And a current, this is the current source, okay? And let's just for fun hook it up to a load like that. And this current source, if it's ideal, has a current I coming out of it. And what this means is that there will always be a current I coming out of the current source, no matter what the size of the resistor is. Let's contrast that with the battery. In a battery, the voltage across the resistor is the same, no matter what the value of the resistor is, if this is an ideal battery. We just talked about it. It's generally not. But if it's an ideal battery, the voltage across the resistor is always the same, no matter what the current is. For a current source, the current across the resistor is always the same, no matter what the value of the resistance is. In this case, we don't know, well, we can easily calculate it, but the current is varying depending on the size of the resistor. In this case, the voltage is varying according to the size of the resistor, right? If it's a big resistor, I'm going to get a big voltage. And a current source will just maintain that current. Now, what about this circuit over here? Just not hooked up to much of anything. What's going to be the voltage across that? Yes?
Constantly changing.
No, not constantly changing. It's going to be infinite. Because it's trying to get a certain current through it, and it can't because there's no connecting path, so the voltage is just going to go up and up to infinity. So that's an illegal circuit. What about this? A battery, voltage V, and a current source, like this. I. Is that legal?
Okay, no more.
There's actually nothing illegal about that. There will be a current I flowing through the circuit. Happens to be going into the battery. The battery in the real world might not be that happy about that, but it's legal. And there'll be a voltage V across the current source. And that's fine. The current source just doesn't care what voltage is across it. It just tries to keep a certain voltage across it. Okay? So that's a perfectly legal circuit. Now, you may wonder why I'm belaboring current sources, because all of you have seen plenty of batteries in your life and you've never seen a current source. It turns out that in modern circuit design, current sources are exceedingly common. If you look inside something where the most complicated circuit we're going to be dealing with today, it's a chip called, not today, this course, it's a chip called an operational amplifier. They have on the order of, say, 50 transistors inside of them. 25 or so of those transistors will be actually functioning as current sources. So they're very, very common. You'll build some in this course later on in the course. And I can't really convince you that they're important until you get to that part of the course, but they're really common. Here's a circuit, okay? It's just got resistors in it. And I contend that it can be reduced down to a single resistor like that. And I would like you guys to all work out on your boards together what you think that single resistance value should be, using some of the rules that we played with before. Okay. About half of you have made progress, and I think most of you who've made progress have come to the right conclusion. But remember, the point of this, I'll say it one more time, is not necessarily to get to the end of the answer, but just to think about how you would get to the end of the answer without my first presenting it to you. But this is a straightforward, if you remember your rules, because I can combine things. What do these two resistors make? 2 ohms. What do these two resistors make? So this is equivalent to this circuit, right? What do these two resistors make?
2 ohms.
And what do these two resistors make?
1 ohm.
And there we go, 1 ohm. Okay? So you probably have done this back in 7B a little bit. And it's important to be able to do it. However, life is rarely this simple. Anybody care to take this one on using the same methods? Don't bother, you can't. So we're going to have to think a little bit more about this. But before we go there, I'd like to talk a little bit about how you draw circuit diagrams. If you have an intersection like this, it's pretty obvious that these 3 wires are connected together, otherwise it wouldn't make any sense. If you have 4 wires together, though, it is not so obvious that the wires are all connected together. By convention, if there's a little dot there, they're connected together. This is, let me do it over here. This is connected. And this, without the dot, is unconnected. It used to be easier. There are certain things that were better in the good old days. In the good old days, this was done like that, which makes it much more obvious that they're not connected. But people don't do that anymore. They use the dots. Okay, with that in mind, let's go back to trying to understand this circuit, okay? First of all, there is one trivial thing that we can say about this circuit. Does anybody want to tell me what that trivial thing is? It involves the 5 ohm resistor over here. It's right, it doesn't really matter, but why? Yeah.
Current usually looks for the easiest path, and 5 ohm resistor is the biggest one next to it.
No. Maybe it doesn't matter is the wrong word. The battery always has the same voltage, right? This is always 10 volts. There's always 10 volts across here, so we always know that there's 2 amps flowing in this direction. There always, always, always is 2 amps flowing in that direction. So it's boring. Everybody see that? So I'm going to get rid of it. But what about this? Well, here, there are a lot of currents that we could consider running around the circuit. For instance, there's some current I0 that's coming out of the battery. There's a current I1 going like this. There's a current I2 going like this. There's a current I3 going like this. There's a current I4 going like this. Do you see the beauty of the way I set this problem up? Never mind. You need to learn to appreciate my aesthetics and my jokes. Okay, and then I suppose there's a current, which I may call I5, maybe it should have been called I10, going down like that. Okay? Oh, yeah, I got drawn an arrow. I don't know which direction those currents are flowing offhand. Maybe some of them are flowing in the opposite direction, but let's ignore that for a moment. In addition to that, there are some other voltages here. Sure, this is 20 volts from here to here, which is 20 volts from here to here, but this point is not necessarily 20 volts, and this point is not necessarily 20 volts either, right? we can't use a simple voltage divider formula to figure out what this voltage is, because the voltage divider formula insisted that there was no current flowing out. This is a voltage divider, like that. Everybody see it? But there's no current going in this direction, so we can't use the voltage divider formula. So we have to do something else. Does anybody remember what we use? Yeah, we use Kirchhoff's laws. Any Russians here? How do you pronounce that?
Kirchhoff?
Kirchhoff? Yes.
Yeah, but I'm not sure if it's V.
I'm sorry?
It's either Kirchhoff or Kirchhoff. I'm not sure. Kirchhoff?
Okay. So we use the unpronounceable Russian name law to figure out what this is. Does anybody remember what Kirchhoff's law, excuse me, I can't. You know, I'm a quarter Russian and I can't remember it, but what we're going to do. There are two types of never mind. There are two types of laws. One of them says that the sum of the currents at any junction is equal to 0. So we can represent that by this. What that means, if I take a junction, here's a junction, any place where more than two wires come together is a junction, the sum of the currents at a junction is equal to 0. And what does that flow from? Something I said earlier at the beginning of this lecture almost. Conservation of charge. You can't have currents suddenly appearing. Okay, so let's do a few of these just for fun. For instance, what? Oh, sorry, I didn't call this I0 in my notes, I called it I6. I6, 0 is going to be equal to this current minus I1 minus I2, excuse me, I4, right? I6 flowing in, I4 coming out, and, excuse me, I1 coming out and I4 coming out, right? So the sum of these things has to be equal to 0, but I've taken advantage of the fact that I know I've defined arrows here, so I can put a sign onto it for coming in or coming out. That's one of these things. Another one I could write down is the sum of the currents at this particular junction. We have I1 coming in, we have I2 coming out, and then we have I3 coming out. So I1 minus I2 minus I3 has to be equal to 0. And then finally, well, not finally, but we have some more. We could, for instance, have the sum of the junction currents at this particular junction. And at this particular junction, we have I3 coming in, and we have I4 coming in, so there's two things with a plus sign, but we have I5 coming out. There are more of these things. For instance, we could sum up the currents at this particular junction, but I'm not going to bother to do that. The system is over-specified. Now, so what have we identified? We've identified 6 variables. 1, 2, 3, 4, 5, 6 variables, right? So how many equations do we need to make this consistent? 6. So I need to come up with another set of equations, another set of 3 equations, which are independent of the first 2, and we're going to use, as soon as I can find my notes, we're going to use the voltage around the circuit law. So, if I take any loop inside of this circuit, one thing about potential is that it's conservative, right? So if I go around a potential and come back to where I started, what has to be the net change in the potential? It has to be 0. That applies for gravity, and it applies for electrical circuits, right? So, let's talk about some of them. Let's do this big one. All right, what do we have here? 20 volts is going to be equal to the voltage drop across here, which is going to be 1 times I1. and then 2 times I2. Now do you appreciate the beauty of my notation? Okay, we've got another voltage loop here. Let's think about what that one looks like. 10 volts is going to be equal to 3 times I3, and then 2 times I2. But we have to be really careful now about signs. So let's think about it. If I start from this point over here, which we could call 0, but 0 is of course arbitrary in any potential problem, and go from here to here, do I gain in potential or lose in potential? I gain in potential, all right? Now, what if I do it the other way? This potential is the same as this potential. So let me go from here to here. Do I gain in potential or lose in potential, assuming I had the right direction for I2? I gain in potential. So this looks like this should be plus 2I2. And then I have to go from here to here, right? I'm equating this potential drop to this potential drop. That's the same as saying, if I go all the way around in a circle, I get 0 potential drop. If I go from here to here, do I gain in potential or do I lose in potential? I'm going in the direction of the current. This end of the resistor is more positive than this end of the resistor, so I'm losing potential. So this is going to be with a minus sign. Well, that's all of the batteries, but I don't need a battery to do this. I can write down 0, and let me take another loop in this circuit. Let me take the loop that goes like this. Doesn't go through any batteries, but so what? I'll arbitrarily, where should I arbitrarily start? I'll arbitrarily start over here, okay? And if I go from here down to here, I will have lost in potential, minus 4 times I4. And then I'm going to go from here to here, gain or lose potential. I'm going to gain potential, so that's plus 3 times I3. And then go from here to here. Do I gain or lose in potential? I'm going to gain in potential, so that's plus 1 times I1. And then, of course, going from here to here, there's 0. So that's another equation, right? So this is 3 equations, and, 3 more equations. So now I have 6 equations and 6 unknowns, and assuming that I picked independent ones, I can solve this, and I will have the solution to this problem. It happens in my notes that I multiplied this times minus 1, so let me do that. That certainly doesn't change anything. So how do we solve this problem? Well, we have an awful matrix equation now to solve via linear algebra, and let me just start to write this out. I'm not going to finish this, for which you'll be grateful, I'm sure. So I have 3 equations whose right-hand sides are 0, 0, 0, 0, and then I have 20, the right-hand side 10 and 0. And then that's going to be equal to a matrix multiplication where this is I1, this is I2, I3, I4, I5, and I6. Everybody remember how this works? And then I just have to put the lousy coefficients here. And for instance, the first row is minus 1, 0, 0, minus 1, 0, 1. And the second row is 1, minus 1, 0, 0, and so on and so forth. I'm not going to fill them all in, but I can just read them off of these equations over here. I don't know if you did anything this complicated in 7b. I think it was hinted at, right? But did people actually do this? A few people say yes. Really this complicated one? That's great. So it's a review for those of you, but many of you did not indicate agreement. But this is how you would solve this. And okay, nobody solves a 6x6 matrix by hand except Russians. So we can easily write. I don't make Russian jokes here either. That's simply true. I can write down what the solution is, and there's a reason I'm writing down this in some precision. This turns out to be 7.273. This turns out to be 6.364. This turns out to be 0.909. This becomes 2.500. This becomes 3.409. And this is 9.773. And that is the solution to this equation. So let's talk about a few things. For instance, what do you think would have happened if I had had the direction of one of these arrows incorrect, pointing in the other direction? Yes?
You get a negative sign in your solution, so probably you hit the wrong arbitrary direction.
That's right. If one of my arrows had been in the wrong direction, all that would have happened was that one of these would have been negative. So there's no, you don't need to devote any thought to that. Okay? However, there is something peculiar about those solutions, and I think some people in the back were noticing what the peculiarity is about one of the solutions. Anybody want to tell me what's peculiar about that solution? The numbers? Well, is one of those numbers special? Yeah, somebody said it. What? Say it louder. I can't see who's saying it. Yes, 2.5. That's a nice number. Now, the mathematicians need not pipe up to say that 2.5 is no more special than 2.537. Because that's why mathematicians go bad. There's no equal sign there. That's why mathematicians go bad. They have no sense of what's important. This is obviously a special number. And if it's a special number and it's such an easy number, we should have been able to see it initially. And in fact, we can. Because look at this outer loop. We go up 20 volts from here to here. We go down the drop across a 4-ohm resistor, and then we go down 10 volts. So what's the voltage across, and then we come back to here. What's the voltage across this 4-ohm resistor? It's 10 volts. And what's the current through the 4-ohm resistor? 2.5 amps. Okay? And so we actually didn't need to solve a 6x6. If we had been a little bit more clever, we could have solved a 5x5. I'm going to cover one more topic today. It comes up quite quickly in the labs. I'd like to discuss the topic of what are called black boxes. So, let's say I have a box full of equipment like this, which is all resistors, capacitors, it could have all sorts of unknown stuff in here. And there are only 2 leads coming out of that box. I can measure the current going into, or perhaps out of the box, and I can measure the voltage drop across those 2 leads, but who knows what might be inside of this box, which is called a black box in the same sense that we have black bodies. We can't see inside a black hole or a black body. We can't see inside a black box. That's all that's meant by that. Now, we really are going to assume that almost anything linear inside of it could be inside of here. That could mean batteries. It could mean current sources, resistors, and if we're willing to sit at a fixed frequency, it could mean capacitors or inductors. And they could be arranged in any pattern. Okay, let me give you an example. here's a black box, but let's say I can open the lid and see what's inside. So what's inside might be a resistor like this, something pretty complicated. It doesn't really matter what I draw here. Okay, could be anything. What the question I would like to know is, what is the relation between the voltage and the current in this black box? All right? It seems complicated. But it turns out that it's not. The relation between the current and voltage here, so remember, this is the voltage that I'm talking about, this voltage and this current. The voltage is always equal to a resistance, which is called R sub Thevenin times I, plus a voltage, a battery, which is called the Thevenin voltage. So Thevenin might have accents. What does this really mean? It means that no matter how complicated the stuff inside is, I can always represent the stuff inside. Here's my black box. No matter what actually is inside there, I can always represent the stuff that's inside there by a circuit, which is just this simple. And this is called the Thevenin equivalent circuit, and it is very important in understanding more complicated circuits. Is that a question?
Yeah. Is there a way of determining whether it's linear inside?
Oh, yes. If it obeys this equation, it's linear inside. Sorry. But that's the real answer to this. It does not work for nonlinear circuits, which isn't really true. There are ways. There are ways to make it work locally, and I'll talk about these ways later when we talk about nonlinear circuits. That, when I first saw this, I think it was sometime in the 1920s. This amazed me. I don't know if it amazes you, but it amazes me. It amazed me. It still does to some extent, but it's actually relatively easy to prove. So I'm going to prove that statement to you. We just did some messy problem, right? Where we wound up with some huge matrix. But the ideas are the same. Even if this problem looks like this, I can certainly do some sort of matrix solution just like I did before. And what is that going to look like? Well, that matrix solution will have this voltage on the outside, right? You can just pretend that that's a battery. It's a voltage, it might as well be a battery. And some current. Now, there may be lots and lots of internal voltages, fine. Right? Internal, some of them may be zero, some of them are not. These are the right-hand side, or the left-hand sides of the equation. And that's going to be equal to some god-awful matrix, whose nature we don't really understand. And then it's going to be multiplied by some other matrix, vector actually, which has got to have our current in it, to be sure, and many other currents. But one thing we know about all of this is that these are just numbers, because this is a linear circuit. And that's all we're ever going to get with a linear circuit, is numbers. So what does that mean? A vector is equal to a numerical matrix times another vector has all sorts of parameters. The only ones I happen to know are V and I. But this is a linear circuit in which I can use linear algebra. And therefore, there has to be a linear relationship between I and V. And there is only one linear relationship. That linear relationship has to be of that form. And if you don't like that as a proof, go back to the math department where you belong. So, the next question is, how can we find these values? I've proved that they exist, but obviously we would want to be able to find them. And it's actually very easy to find them. How do we do that? We have a black box, right? If we just don't hook up these two leads to anything, but just measure, that's supposed to be a voltmeter, the voltage here under the condition of no current, then this is 0. The voltage that we measure is simply the Thevenin voltage. Right? So if we, what's called, make an open circuit, the open circuit voltage of the black box will be the Thevenin voltage. Everybody see that? How do you think we might measure the Thevenin resistance? I'm sorry?
Make the Thevenin voltage 0.
Yes, not the Thevenin voltage. We don't control what the Thevenin voltage is. That's inside the box. But we do control what the voltage here is. We can short these two wires together and make them 0. That's called the short circuit condition. And when we make the short circuit condition, this is 0. We've already measured the Thevenin voltage. And so we can measure the current. And the Thevenin resistance just pops out of the division between the previously measured Thevenin voltage and the currently measured current. And we're in business. So we've measured those parameters. It's really easy to do experimentally. The important thing is that it's fully equivalent. So what exactly do I mean by fully equivalent? Well, I've got my Thevenin circuit like this, right? I'm perhaps belaboring this point, but what this means is that I can hang anything here. This is a lousy way to draw a circuit diagram, by the way, but you should never have diagonal resistors like that. But I can draw anything here, and it doesn't matter. This Thevenin stuff stays the same. It just doesn't matter. Once I reduce something to a Thevenin equivalent circuit, I'm done with that part of the circuit so long as it's linear. And that can be a great simplification. So let's do something. I'm going to close this out fairly soon, but I'm going to close with just doing an example from of a practical example. Let's say that what's inside the black box is this. Okay, so this is my black box, and we don't have access to this experimentally, but we have the circuit diagram. So I'm going to ask you as the final work it out together exercise for today, tell me what the Thevenin voltage here is from the circuit diagram.
No,
All right. Anybody think they know what the answer is?
I thought it would be 5 volts.
It is 5 volts. Anybody want to tell me how you can see that immediately? Okay, that's hard. Remember I was telling you that part of what you learn through this course is to recognize circuit elements like voltage dividers. Look at this circuit for a second. I'm going to keep the same topology, but I'm going to redraw it. Here's my battery. Here's this resistor. Here's this resistor. Here's a 1 ohm resistor. And I'm measuring this voltage under the condition that there's no current here. What is this? What is this voltage under the condition that no current is flowing here?
Voltage across the 2 ohm resistance.
That's right. But more precisely, it's a voltage divider, right? This voltage, 10 volts, is just going to be equally split between these two halves. So this is going to be 5 volts and this is going to be 5 volts. Therefore, this voltage is going to be 5 volts. And that's the Thevenin equivalent resistance. Excuse me, the Thevenin voltage. And I know that very few of you, or if any of you, caught that immediately. But it's like, well, I don't want to be as grandiose as to say that it's like reading music. To me, if I see a musical score, sadly I don't, I'm not a musician, but to somebody who's a musician, they look at a score and they recognize things. Here, once you've done this for a semester, you'll recognize things, like voltage dividers. And you'll be able to say the answer is something without having to think about it. It just becomes automatic. Okay, so we've gotten half of what we need for the Thevenin resistance. Excuse me, for the Thevenin circuit. We have the Thevenin voltage. Now we would like to find the Thevenin resistance. And the way we could do it is just to imagine doing it the way I suggested that you do it experimentally, which is to short these two things and measure the current that comes out. I mean, mentally short this, like mentally draw a wire from here to here. Okay? We could do that, but there's another trick, and I'm not going to prove this trick. But what the other trick says to do is to take all of the voltage sources and mentally short them. Just take them out of the circuit and short them. Remove them out of the circuit and put a short wire between them. Take all the current sources, there are none in our particular example, and just take them out of the circuit, open up the circuit. And if we do that for this particular circuit, what we're going to have is this, right? I took out the battery that was here and just shorted it. The Thevenin resistance is the resistance that we would see looking into these two leads. I'm not going to prove this, I'm just asserting it. But this is obviously trivial, because these two resistors look like, these are two 2 ohm resistors in series, so that looks like 1 ohm, this is 1 ohm. So this just looks like a 2 ohm resistor. So the Thevenin equivalence circuit of this thing is something that is significantly simpler. A 5-volt battery and a 2 ohm resistor. Now obviously if we had something more complicated inside, the contrast between this and that would have been greater. Okay, so next time we're going to discuss impedance and then start talking about complex impedance and nonlinear impedance